Well, hello again. We're going to do hypothesis testing for two proportions, a two proportion z-test. Basically, we're looking at, is there evidence of a difference between these two proportions or two groups of individuals? So remember, our steps for a hypothesis test is we define the parameter. For a two proportion test, there will be two parameters to define. We name the test and check conditions. I also forgot to state we also have to write our hypothesis statements. We name the test and check conditions for step 2. We calculate our z-score and p-value for step 3, and then we write our conclusion to our test in step 4. So same general 4 steps. Our conditions will be a tad different, and then we will have 2 parameters instead of 1, and our hypothesis statements will be about 2 parameters instead of 1. So real quick, conditions for two proportion hypothesis tests are pretty much the same as for two proportion confidence intervals. We check that we have independent random samples, so they're both random or representative of their individual populations, and we need to at least assume or know that the groups are independent of each other. So they're taken separately, not related, etc. Then we check 10% condition for independence between trials. Again, that's different from independent samples, but 10% condition is our sample less than 10% of the population. We do that separately for both groups. Remember, we have that exception if a problem is an experiment. Instead of really looking for are they random samples, we're really just checking that the treatments were randomly assigned, because that gives us independent groups. Sometimes in an experiment we have a random sample, but it's just not very common, so it's not something that we worry too much about. We can assume that it's a representative sample, but we don't worry too much about that. And then we also don't need to worry about the 10% condition, since it's not actually a sample taken from the population. But always, 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 we should be checking success failure condition. So NP and Q for both groups needs to be greater than 10. And this would be P hat, because that's all we would really truly know is the sample proportions. Again, it's easier to sometimes think of it as the number of successes and failures. So hypothesis statements. When we are dealing with two proportions, my null hypothesis is that there's no difference or no change between the two proportions. So your null would be that P1 equals P2, that the two proportions of the two groups are equal in terms of what we're measuring. You could also write that as P1 minus P2 is equal to 0, that the difference between the two groups is equal to 0. That would work as well. Your alternative hypothesis is basically that one is greater than the other, or less than the other, or not equal to the other. It's basically what we think might be true based on what the problem asks us to show. In terms of this proportion. So less than, greater than, or not equal to. Again, we could write that as a difference compared to 0. P1 minus P2 is less than 0, or greater than 0, or not equal to 0. It's okay to write it either of those ways, but that's essentially what our hypotheses are. Remember, we need to define our parameters first, so we're defining P1 and P2 before we start using them in our hypothesis statements. You can also choose to write your hypotheses out in words completely if you want to. So formulas, we're not going to spend too much time on this, because the formulas for a one proportion z-test is what that should say is kind of complicated. We still have a basic formula for a z-score. This says confidence interval. It should say z-score. Standardized score is your statistic minus your parameter divided by standard error of statistic. For a problem like this, we're testing the difference between two proportions. This is what the top part of that would look like. So the difference in the two statistics, so the sample proportions, minus P1 minus P2 would be the null hypothesis difference, which is always going to be 0 for us. So the second part will always be 0, because that's always our null hypothesis. Then we have the stuff on the bottom, which is where it gets complicated. Because we are assuming our null hypothesis is that the two proportions are equal, we kind of look at this as a combined overall proportion of success, and then divided by sample size. It's definitely a little bit more complicated, and because it's different from what we normally do, I'm just going to encourage that we don't really worry about writing out the z-score for a two proportion test. This is the formula that would be used but don't worry about it. We're pretty much just going to make sure and let the calculator do the work. We're just going to make sure and write 2 prop z tests somewhere so that we don't actually have to write the formula. I said the formula will pop up in multiple choice questions. It typically doesn't for a test, a 2 prop z test. I love how this says 1 proportion z interval. This is for 2 proportion z test. I just apparently can't change things. So there's that. Let's do a problem. So a driving school owner believes that instructor A is more effective than instructor B at preparing students for the state driver's license exam. An incoming class of 100 students is randomly assigned to 2 groups, each of size 50. One group is taught by instructor A, the other is taught by instructor B. At the end of the course, 30 of instructor A students and 22 of instructor B students pass the state exam. Does the study provide evidence that instructor A is more effective in his teaching methods than instructor B? So one thing I want to mention here again is that obviously in our sample, the sample sizes were both 50. Clearly, instructor A had a higher number of students pass the state exam. So if we were just saying for this one sample, for this one group of students, instructor A is more effective, obviously. But what we're saying is for all students, for any group of students that there ever could be, is there evidence that instructor A overall would be more effective in general for all students than instructor B? So we have what's true for a sample. We're using that to try to estimate or come to some conclusion about what could be true for the entire population of all students who would ever take this course. So that's kind of what our thought process is in going to this. So I'm going to start by defining my parameters. That's step 1. We're going to state. We're going to define our parameters and write our hypothesis statements. So I'm going to write this as PA and PB since they gave me instructor A and instructor B. So instructor A or PA would be the proportion of instructor A students who would pass the state exam. Notice that I said who would pass. We're not talking about this specific group of students, so it's not who did pass. We're saying of all students that could ever have instructor A, it's the proportion of them who would pass the state exam. PB is the proportion of instructor B students who would pass the exam in general in the future of all the students who could ever take it. Our null hypothesis for a 2 proportion is always that the 2 proportions are equal. So PA equals PB. And then in this example, I want to provide evidence that instructor A is more effective. So more effective would mean that a higher proportion of instructor A students pass the exam than instructor B. So my alternate is that PA is greater than PB. All right, I also wrote it over here as the difference greater than 0 or equal to 0. It's okay to write how I have it on the left. I just always like to include. That's what it would look like as a difference. All right, we are doing a 2 proportion z test. So now we're going to do our conditions. So our 3 conditions, firstly, we need random samples, but we also need them to be independent of each other. So this is where I might come to a pause because it doesn't really say that they are a random sample. It's an incoming class of 100 students. We could probably assume that these 100 students are like representative of all students who would take this class. And that's reasonable to say, but it's pretty clear from the beginning, this is an experiment. We have 100 students, we have randomly assigned them to their 2 different groups. So what I'm going to say here is that we're given that they're assigned to instructors randomly, which is giving us 2 independent groups. That random assignment gives us independent groups. So even though they're not a random sample of students, because it's an experiment, I'm not going to worry too much about that, but I do want to point out that they're randomly assigned because that's what gives us the independent groups of students. I'm also not going to worry about 10% because these weren't a random sample or any kind of sample from the population. So 10% doesn't truly apply, but it would be okay to check it. I could say assume 100 students is less than 10% of all students who will ever learn how to drive. It would be okay to say that. We could also say individually, assume 50 is less than 10% of all students who would ever be taught by instructor A and instructor B. It'd be okay to check that. For our NP and Q success failure condition, basically we need the number of successes and the number of failures in each group to be greater than 10. So for group A, 30 passed, and then out of 50, so 20 didn't pass. For group B, 22 passed, and out of 50, so 28 didn't pass. All of those are greater than 10, so we know we are okay to use a normal model for this problem. So that's my step 2, which is plan, name the test, and check conditions. My third step is going to be the calculate the math. So for this, I'm going to go straight to my calculator because I really don't want to try to mess with that formula because it's so different. I'm just going to go straight to the calculator. So I'm going to go to stat and tests, and then we are doing a 2 proportion z test. So 2 prop z test number 6 is where I'm going to go. Again, I have these options of x1, n1, x2, n2. Notice that they didn't ask us for a like a null hypothesis like it did for a 1 prop z test, and that is because it assumes that your null hypothesis is that they're equal for this test on the calculator. So I'm going to put in for group 1, which I'll say is instructor A. We had 30 pass, so 30 out of 50. So N1 is 50. For group 2, which is instructor B, 22 passed out of, again, 50. We do have to choose our alternate hypothesis. So we wanted to show that P1 is greater than P2. So I'm going to go over here and choose that third option. And then again, we have the option to calculate or draw. I always like draw because I like that it gives me a graph of what's actually happening. So this graph that's shown is the sampling distribution for the difference of P1 minus P2. And we were wanting that difference to be greater than 0. So it's shading over here to the right. So we are given a z-score 1.6013, and we are given a p-value 0.0547. So those are the things that we would want to make sure and write down on our paper. So z-score is 1.60, p-value is 0.0547. And that's really it for our calculate step. It's all we really have to write. Because I wrote 2 proportion z-test over here, that kind of takes away the need to write out the formula, but I need to make sure and write out the z-score and the p-value. So now we're ready for step 4, which is to conclude. So we would talk about our p-value in comparison to the significance level that they did give us. So 0.0547 compared to 0.05, it is greater. And when p is greater than alpha, we fail to reject our null hypothesis. So my first sentence in my conclusion is since our p-value is greater than alpha, 0.0547 is greater than 0.05, we fail to reject our null hypothesis, H0. And if we are failing to reject the null, that means we do not have evidence of our alternate. We fail to reject the null means we're stuck with the null. We do not have evidence of the alternate. So I would say there's not evidence to suggest that the proportion of students who would pass with instructor A is greater than the proportion of students who would pass with instructor B. Or in other words, we don't have evidence that instructor A is more effective in teaching methods than instructor B. In other words, this difference that we're seeing in this particular sample is not different enough to make us think there's a huge major difference. It could just be kind of a fluke difference. The next time they do this course, it could maybe easily be the other way around. So essentially what we're saying, it's different, but it's not different enough to make us think it's significant. All right. So when we interpret p-values for a 2 proportion, there's a lot going on. There's 2 different samples essentially that we're dealing with. So when we interpret it, it can get really messy really fast. So I always try to simplify how I say the p-value for a 2 proportion. So I'm going to say, as always, start by saying, assuming the null were true, if the null hypothesis were true, so assuming the 2 instructors are equally effective, is what our null hypothesis said, there's a 0.0547 probability of randomly or by chance observing a difference in pass rates like the one observed in the study or a difference more extreme. So I'm basically saying the p-value is the probability of getting what we got in the sample or something more extreme. The what we got in the sample is the difference in sample proportions that we saw. And notice I didn't actually say what that difference was because that was a lot of numbers and it's going to make the sentence even more complicated than it already is. So I just said observing a difference like the one we saw or a difference even more extreme, meaning a difference that's even greater, even more different from each other. So 0.0547 probability of just by chance getting a difference like we saw in the study or a difference more extreme. So there is a second example in here that we're going to work on more in class. So I'm going to leave it up here on the screen for you to look at, but I want to save this one for class time just to review it and kind of practice a little bit more. So that is it for this lesson. I will see y'all next time.